curved space. And then if you draw a triangle, the triangle, you know, and if you're like a deity and you can see the triangle, right, it has less than 180 degrees because of the curvature, right? Whereas positive curvature is like, you know, more than 180 degrees, right? Only these people don't see this curvature because that was a terrible triangle. I'm very sorry about that. I could have done better, but, you know. Make one? Oh. It was very hard to do. It's like somebody's logo, too. That's pretty good. That's got a lot of... Right. So positive curvature, negative curvature, right? Now, what's interesting is that they tried to do, and this is a classic example of sampling error. There's another variable that explained this data, but they didn't know it at the time. Okay, but what they decided to do is there's quasars. Quasars are these very strong radio sources, and we can identify them very, very far away because they are black holes that are eating tons of stuff. Right? That's what a quasar is. That's on the test. Okay, so if space is flat, what? Repeat that? No.
What did you just say?
About quasars, what quasars are, right? Okay. That they're black holes that are devouring material. That's how they radiate light, right? If you have flat space, and the quasars are evenly distributed throughout the galaxy or throughout the universe, right? And you flatten the space. Well, flat space is already flat, so there's no distortion. The galaxies or quasars are spread out evenly. Okay. If you have positively curved space and you flatten it, in order to flatten it, you've got to make little cuts in it, don't you? Yeah? Okay. And this is, by the way, the opposite of like the Mercator projection, which is what you see on the wall. The thing that makes, I think it's the Mercator projection that makes Greenland look bigger than Africa. Yes? Have you seen those maps?
It actually is big.
Yeah. Yeah, well, of course, right. Because here's Greenland, right? Africa, right? Yeah, no, it's not, right? So it's not. No, not. More than you all the time. But anyway, this projection, the other thing you could do, and nobody does this because most of the landmass is at the equator, is that you could cut the map up and have these gaps in the map at the equator, right? Notice that makes some of the space out there is not really there, right? That makes the space farther. The farther you go from the Earth, the less represented that space is. And so if you map where the quasars are, it'll appear that more of them are close to you, fewer are farther away because this space is just underrepresented, right? Okay, that's kind of a weird thought. Are we thinking about this? Here we go. Okay, if space is negatively curved, the opposite happens. When you flatten it, you actually have folds here, right? You have to flatten a satellite, you have to actually fold that space. And so the farther away you go, the more space actually is, what you think is a certain amount of space is actually more than that space because it's actually space folded on top of itself, right? Okay, and so if you took data from that, you would say, gee, there's more quasars farther from the Earth than there are close to the Earth, yes? What's the obvious experimental problem with this effort? What is true about quasars?
They're big and bright.
They are big and bright, and they eat matter at a fantastic rate and are not sustainable. And so once in the universe, when the universe was young, the quasars were many bright quasars, and now as the universe is old, there are fewer bright quasars, correct?
Yeah.
Quasars themselves evolve over time, and with a telescope, you cannot separate space and time, right? And so distance becomes time. And so this is what we see. This is what they saw. They saw strong evidence of negative curvature, right? But this is distorted because you're looking back in time. There were more bright quasars. Now there's fewer bright quasars. Yeah? So yeah, this experiment that I spent 10 minutes explaining is flawed, right? Although it helped them get this whole notion of quasars, right? It's like, oh, look at that. Right, so that's sort of an interesting thing, right? Okay, so basically cosmology, and Timothy Ferris talks about this. There's a search for three numbers, right? There's the Hubble Constant, which is the current rate of expansion. That's what we think it is, right?
So wait, which one should we use on our test? 74.1 or 71?
Oh, I don't know. I'll tell you what to use on the test.
Sounds good.
Right. Always use whatever they tell you, right? Even if it's totally outdated. Yes, I will use that Hubble Constant, and I will not question it. Okay. Then there's Q naught, and this is the deceleration parameter. This is actually the rate of braking due to gravity. And then there is lambda, right? Because we've got to use the same letters over and over and over again, right? This one is the cosmological constant. It's like an anti-gravity, right? Nobody really likes this one, But it seems like something like anti-gravity is going on. So what's funny is that Einstein put it in general relativity, retracted it, and now something like that's going on, which is kind of funny. That's not irony, though. For it to be irony, it has to be that you're trying to make it not happen, makes it happen. Yeah?
How do you know that's not how it happened?
That's a strict interpretation of irony, right? Yeah.
Didn't they only discover the cosmological constant after Einstein predicted?
Yeah, but he didn't make it happen, right? Yeah, pretty sure. Pretty sure he's not a deity or something like that. Okay, now for your convenience, we can talk about omega, which is like the density. When they talk about the density of the universe, it really is this very subtle combination of these constants, right? And so this is omega less than 1, a density less than 1, right? Where 1 is the critical density. Critical density is the one that makes us expand and just stop, right? And then the final one, and this will warp your mind, right? Is that omega more than 1, more than critical density is. So when we talked about density, this just means that it's got enough mass to cause the universe to recollapse. Spatially, it means that it's got enough mass to make positive curvature, right? And apparently, if it doesn't have enough mass, then the universe itself is, this is really bizarre, right? Okay, is negatively curved, yeah? I can't picture it either. Are you picturing it? I'm trying. Oh, I can't do it either. Okay, there it is. There's one kid in the class that's going, yeah, no, I can picture that. There you go. Right, so this is, you can label that same chart, omega less than 1, omega equal to 1, more than 1. Or you can say less than critical density, equal to critical density, more than critical density, right? You can also label it negative curvature, flat, positively curved. You can also label it more than escape velocity, less than escape velocity, exactly escape velocity. So many labels, right? Which is the right one? Well, it depends on what you're trying to get at, right? Are we right arrow ready? Right? So as far as we can tell, omega is almost 1. We think it's exactly 1 because if it is 1, this is the only value that would not change as the universe expands. If it's 1, it stays 1, and 1 is like a balance point, right? It will always be 1. It is 1. It was 1. And so we are observing the universe not at a special time, but just at any time, right? Because it's 1, and it was 1, and it will be 1, right? That's kind of cool, right? So the cosmological principle states that if you have a theory that depends on, the only way it's right is that you have a special set of conditions. It's probably not right, right? And so an omega of unity is not special. It's just, it's what it is, what it was, what it will be, right? And this is, how do you tell this? Well, what they can do is they just do a little geometry, okay? Let's look at that fiery wall. On that fiery wall, some distance from us, right, there is, we're looking back in time, right? So we know that this is, the decoupling happened at 0.37 billion years, right, roughly. I think isn't that what we had, right? And then this is 13.7 billion to Big Bang, which happened behind the fiery wall, right? When we look at this fiery wall, there's features on it. See the features? That's the fiery wall. Those are the features, right? And so what they can do with this is they can look at the size of these features. Now, obviously, not everything's the same size, but there's a granularity to it. There's a statistical method, right? And so what they can do is they can draw little triangles. Here we are observing this, right? You know, here's one side of a triangle. That's the other side of a triangle. Space apparently was curved, right? But it's not, right? Can't we measure, if we know this length of this side here, can't we measure all the interior angles and check Euclidean geometry, right? How do we know the size of this? Do we know the age of the universe? And do we know that causation can't travel faster than the speed of light? Yeah, there we go, right? These events are caused, they have a central locus and they spread from there at the speed of light. And we're seeing these things at this exact age, right? And so we know the size, sort of the average size of these things. And so we could measure these angles here. As far as we can tell, flat as a board. Why is that, though, do you suppose? The Earth is flat. I'm looking outside. It looks flat. It's flat. I can even sit on the top of Mount Hood and it looks flat. Because why?
How do you explain that? It goes down, it goes up.
Well, this is local curvature of space-time caused by bulldozers, right? So what's the deal? Why does it?
It's too big.
Yeah, it's a lot bigger than we can observe, right? So this is the deal. we basically, in an attempt to measure the curvature of the universe, we detected it's flat, and that's because we're looking at a